This is the last of Chapter 8, Chemical Reactions in Aqueous Solution, and this lecture is about oxidation reduction reactions. An oxidation reduction reaction is a reaction in which electrons are transferred from one substance to another. For short, you'll hear them called redox reactions. They got their name, oxidation reduction, because many of them involve reaction with oxygen, not all of them. So in general, if they are reacting with oxygen, the substance that gains oxygen, they say, or we say, has been oxidized, which makes sense, right? But the definition of the type of reaction has expanded, so they do not all involve oxygen. All right, so the current definition, more broad definition, is oxidation is when an atom loses an electron, okay? So remember, electron's negatively charged, so when an atom loses an electron, it's left with a positive charge behind, right? We call that oxidized. A reduction occurs when an atom gains an electron, okay? So in this kind of picture here, the orange oblong thing would have been oxidized. It's losing an electron, and the purple one would be reduced, gaining an electron. And they occur hand in hand, okay? If you have a substance that's giving away an electron, there has to be something else there to accept it. A mnemonic for remembering that, there are several, but the one I like is Leo says Gur. And if you lose electrons, you have been oxidized. If you gain electrons, you have been reduced. Students always tend to get a little confused by this because gain doesn't sound like reducing, right? They seem like they're diametrically opposed, so just kind of pay attention to that. All right, so a really simple example of an oxidation reduction would be formation of sodium chloride, table salt, from its neutral elements. So you can see in this case, the neutral sodium atom gave away an electron to the neutral chlorine atom to make the sodium cation and chloride anion. So the substance that gained electrons is the chlorine, and so chlorine was reduced. Sodium is the substance that gave away the electrons, so sodium was oxidized. It's really easy in this reaction to see what's been oxidized and reduced. It is not always so easy, okay? You have several reactions which don't even have ions or charges involved, and you still have to figure out where electrons have shifted. So in the more complex redox reactions, in order to be able to determine what's been oxidized and what's been reduced, we assign something called oxidation numbers. They are not real charges. I want to emphasize that. Okay, so if we assign an oxidation number of +1 or +2 or -3 or -4, those are not real charges. Okay, it's a way of, it's really a bookkeeping. It's a way of kind of tracking almost like electron density, or where an atom's valence electrons has ended up when it's made bonds and involved in a compound. So there are several rules that go along with assigning oxidation numbers, so we're going to go ahead and go through that first. Okay, the first rule is when you finish assigning oxidation numbers in a compound, let's just randomly take methane, natural gas, the oxidation numbers must add up to be the charge of the compound. So this is a neutral compound, right? There's no overall charge. So when you assign oxidation numbers, they better add up to be 0, okay? And you'll see, but in this case, each hydrogen is +1, so the hydrogens all together are +4. Carbon has an oxidation number in this compound of -4, And so just adding them all together, we get an overall charge of 0, which is good. So you want to do that when you're done assigning oxidation numbers. Now, if you have a substance that has a charge, let's say the nitrate ion, then whatever oxidation numbers you assign to nitrogen and oxygen, they better all add up to give the overall charge of the compound, -1, okay? All right, so that's rule 1. Rule 2, any elements that are on their own in their standard state, how they exist in nature, has an oxidation number of 0. Okay, so magnesium, neutral magnesium, 0. The halogens and hydrogen, for example, exist in nature as diatomics, 0. We have some weird ones out there. Phosphorus tends to exist in a natural state, P4 phosphorus together, 0. Okay, so any element in its natural state is going to have an oxidation number of 0, okay, because it doesn't have to share with anybody. So, all right, number 3, rule 3. The oxidation number of an ion is the same as its charge, okay? Really simple here. Table salt, sodium chloride, we know is made up of the sodium cation and the chloride anion, okay? So in this case, when you have an individual element with a charge, the charge becomes its oxidation number. Okay, so sodium would also have an oxidation number of +1. Chlorine would have an oxidation number of -1. All right, this set of rules, this is a continuation of the rules, but they're a little bit more complex. So. Nonmetals, we have learned when we look at the periodic table, right? If you go to the right of the stair step, we have nonmetals, right? And we have learned that when making ions, full out charges, the nonmetals will always be negative, right? And that metals will be positive charges. Okay, so I want you to remember that oxidation numbers are not charges, okay? So they're kind of weird. So you have some nonmetals, when you're assigning oxidation numbers, they'll tend to have negative oxidation numbers, like nonmetals tend to be negatively charged ions, but there are quite a few nonmetals that will end up with a positive charge also. So you'll see things like chlorine with a +3 oxidation number, just some weird ones. So I want you to be aware of that. The one exception to that, and it's because it's so electronegative, it's not going to share with anybody. Fluorine will always, 100% of the time, have an oxidation number of -1. Okay, it's the only halogen that won't budge. It'll never be positive. All right. Oxygen. Now this is your go-to. These 2 rules right here, the last 2, are your go-to rules. So when you're presented with a compound, and let's just say let's make it a little bit complex. Let's see, you got that, acetic acid. And you're asked to assign oxidation numbers to every atom in there. You got to figure out, where do I start? I don't even know where to start. Well, you start with these last 2 rules. Oxygen, 99% of the time or more, will have an oxidation number of -2. Okay. There is one exception, which I don't think you're going to encounter, but just so you're aware of, it's when oxygen is involved in a type of bond called a peroxide bond. And that's when there are 2 oxygens together, single bonded to each other. So remember, molecular oxygen is double bonded, okay? So that's not the peroxide you have in your house probably is that. But the oxygen in peroxide has an oxidation number of -1, but every other place it is -2. And so if I were starting to assign oxidation numbers in this acetic acid, I almost always start with oxygen. I'm like, okay, I'm going to give the oxygens -2 because I don't see any oxygen-oxygen direct single bond linkage, okay? And then the last rule, which is another one that'll help you with compounds, is hydrogen 99% of the time is +1. As usual, there's one exception, and that's when a hydrogen is bonded directly to a metal, which is unusual, and I don't think you're going to encounter that. So, yeah. So it gets a lot easier. It's kind of like a puzzle. And the more pieces you have, the easier it is to or finish the puzzle. All right, I think I mentioned this before, but just it's worth repeating. Where you have oxidation, you also have to have reduction, okay? Can't have one without the other. So I'm going to go through these examples and then encourage you to try some on your own. So these are they're pretty easy. So carbon dioxide, let's do this one, okay? So I always start with oxygen. And what I do is I assign the oxidation number for one individual atom of the element. So forget the subscript for now, for this second. I'm going to give oxygen -2, each oxygen. And then I do the math below the compound. So I know I have 2 oxygens, so oxygen total in this compound is contributing a -4. I also know that this compound has no charge, so I know whatever oxidation numbers I assign better add up to be 0. So since the 2 oxygens together contribute -4, I know this one carbon must be assigned an oxidation number of +4. All right, and so that works out. +4 -4 is 0. So what you're going to need because we're ultimately going to balance oxidation reduction reactions, is you are going to need to know the oxidation number of every single element. And so I would keep them all on the top of the atoms. And again, just put the oxidation number for one single atom up here because that's what matters. Okay, we're looking for oxidation numbers that change from the reactant side to the product side. All right, so now on the next one, the nitrate ion. Again, I'm going to start with oxygen. I'm going to give it a -2. I'm going to do my math in the bottom. I know there are 3 oxygens, so 2 times 3 is 6. So I know oxygen collectively contributes -6 to the overall oxidation number. I know also that nitrate ion has an overall charge of -1, so I know that when I add together all the oxidation numbers, they better add up to be -1. So what does the nitrogen atom, what oxidation number must the nitrogen atom have so that whatever it is, -6 equals -1? That would have to be +5, right? +5 -6 is -1. So the oxidation number for nitrogen is +5. The oxidation number for each oxygen is -2. Hopefully you're getting the hang of that a bit. All right, let's move on and do iron 3 oxide, rust. All right, starting with oxygen again. You see the value of oxygen? -2. And oxygen overall contributes -6. 2 times 3 is 6. All right, so now be careful because this is the first time we have an example where we have 2 of the other atom also. So I know that collectively these 2 iron atoms must have contribute to the oxidation number of +6. All right, but since there are 2 of them, each of the iron atoms must have an oxidation number of +3. And now I've got to make sure, right? Iron 3 oxide has an overall charge of 0. So I'm going to check, and yes, +6 -6 equals 0. That's good. So these are the oxidation numbers you're interested. Again, the ones on top for one single atom. All right. And when you are presented with a chemical reaction, you will assign oxidation numbers to every single atom and every single compound on both sides of the arrow. So, and then you'll look for any changes. All right, the last one that I have here, sulfur hexafluoride. So there's no oxygen or hydrogen to help us here. There was one other like hard and fast rule, and that is that fluorine is always -1. And since there are 6 fluorine, collectively they contribute -6 to the overall oxidation number. And since this compound is neutral, I know that overall oxidation numbers must add up to be 0, which means that sulfur has to be +6. Okay, that is it. Here are some for you to try, and I'm not going to work them out because if you're in my class, you need to go to Go Formative and see how you do with those. Now, let's look at an overall chemical reaction that is a redox reaction, okay? We want to assign oxidation numbers, and then we want to determine what substance has been oxidized, which substance has been reduced, and how many electrons have been transferred. So this is a very simple example. Right, so you always start by assigning oxidation numbers. So remember, elements, neutral elements in their standard state are 0. Ions, the oxidation number is simply what the charge of the individual ion is. Here's another neutral element at standard state. So now that you have assigned oxidation numbers, you can figure out what's been oxidized and what's been reduced. So let's look at what has happened. Zinc has gone from an oxidation number of 0 to an oxidation number of +2. What does that mean? That means that zinc has lost 2 electrons. Remember that electrons have a negative charge, right? So when you take electrons away, what are you left with? You're left with a positive charge on the substance. So when you lose electrons, remember Leo, lose electrons, oxidized. So zinc has been oxidized. And if something's oxidized, something else has to be reduced. So let's look at copper. It's gone from oxidation number of +2 to oxidation number of 0. So it has gained 2 electrons. It's gotten more negative or less positive, however you want to look at it. So GER, Leo says GER, gain electrons means reduced. All right, so the one of the next questions that'll come up is how many electrons have been transferred? It's pretty easy here. It's very easy here to see that 2 electrons have been transferred, right? But it won't always be that easy. I like to tell students a couple of classifications of chemical reactions that are either always oxidation reduction reactions or never oxidation reduction reactions, because it saves time. If you're on an exam and you have to assign oxidation numbers for every single atom in a reaction, it's very time consuming. So combustion reactions are always oxidation reduction reactions. Okay, so that's kind of just a good thing to put in your back of your head. And by the way, double replacement reactions, the ones we just talked about, precipitation reactions, acid-base, they're both types of double replacement. They are never oxidation reduction reactions, okay? All right, so we're going to look at a combustion reaction and just kind of prove that it's a redox reaction. So we're going to start by assigning oxidation numbers. So let's look at methane. I'm going to give hydrogen +1, which means in this case, for CH4 is neutral, we have to give carbon a -4. Oxygen is diatomic in its natural state, has an oxidation number of 0, as all elements in their standard state do. Carbon dioxide, we are going to start with oxygen by giving it an oxidation number of -2, which means carbon has to have an oxidation number of +4 in order for the overall oxidation numbers to add up to 0. And let's see, water, we're going to start the same way, right? So -2 for the oxygen, and we'll put that up here, which means, and hydrogen's almost always +1. Of course, there are 2 hydrogens, so they collectively contribute +2. All of the oxidation numbers add up to be 0, which is great because water is neutral. All right, so at this point, when you have assigned oxidation numbers, again, you want to look at each atom and see if its oxidation number has changed in moving from the reactant side to the product side. See, carbon has gone from -4 to +4. What has happened to it? It has lost electrons, right? If you're getting more positive or less negative, you've lost electrons. It's lost 8. That's a lot. Leo, okay, so lose electrons means oxidize. Carbon has been oxidized. Now, do you remember when I told you the original definition of oxidation reduction reactions, how it got its name? And I said that many of the reactions involved oxygen, as does combustion, and that the substance that's been oxidized, which is carbon in this reaction, end up with more oxygen, which it does. Okay, so that's another easy thing to remember. If you see an element, an atom, become attached to more oxygens, that is the element that has been oxidized, always. Okay, so again, that's just kind of a quick shortcut to nice to be aware of. Okay, so if something's been oxidized, something else has to be reduced. What has been reduced? Well, hydrogen stays +1, so nothing has happened to it. Oops, kind of off center there. Okay, so let's look at oxygen. Oxygen had oxidation number 0 on the reactant side and -2 on the product side. So oxygen has gained electrons, gained 2 electrons. Okay, so oxygen is what has been reduced. Alrighty, so that is it for, that's just a common example. Another type of reaction that is always a redox reaction is single replacement. You may have been exposed to those in the past, but if not, what you will see in a single replacement reaction, the way to understand them, is that you have one element on its own reacting with a compound. Okay, so you have one element and one compound on the reactant side. Then you have a different element and a different compound on the product side. So do you remember that double replacement was you started out with 2 ionic compounds and you ended up with 2 different ionic compounds? Okay, single replacement is related in that these two switch partners, right? So anyway, single replacement reactions are always redox reactions. Just erasing all my scratchings here. Okay, and I don't know, pretty much when you see a single element by itself as a reactant, it's almost always a redox reaction, because remember, single elements have an oxidation number of 0. And so once they make a compound, it's rare for them to have an oxidation number of 0 in the compound. So anyway, single element by itself is almost always a red flag that you've got a redox reaction. So let's look at what has changed here. The copper's gone from 0 to +2. It's been oxidized. It's lost electrons. What's been reduced? Let's see. Chlorine has -1 here and -1 here. It hasn't changed. How about hydrogen? It's gone from +1 in the reactant side to 0 because it's on its own on the product side. So hydrogen has been reduced. Okay, we're close to the end now, okay? All right, so this is a really common type of multiple choice question that I can almost guarantee you'll be asked on an exam with this subject. Which of the following are redox reactions? And so what that's going to require is that you assign oxidation numbers to every atom and see if any of them have changed. I will do the first one for you, but then I want you to go through the rest of them. And again, if you're in my class, you'll want to go to Go Formative and finish. So this one's a little tricky, so I just kind of wanted to do it for you. Mercury ion, and remember I said that ions, their oxidation number is simply the charge on the ion. This one's a little tricky because the mercury ion comes as a double, 2 mercuries, okay? So what that means is the oxidation number of each individual mercury is only +1. All right. So for this polyatomic, if Oxygen is given a -2, and hydrogen is given +1. Those add together to give me overall oxidation number of -1, which is good because hydroxide has a -1 charge. So it added up the way it should. So oxygen here has a -2. Each mercury is +1, right? So if you do the math in the bottom, +2 for mercury, -2 for oxygen equals 0, which is good. Mercury oxide doesn't have an overall charge. Water, oxygen's -2, each hydrogen is +1. So now look and see if any of the atoms have changed their oxidation number from the reactant side to the product. Mercury has stayed the same. Oxygen has stayed the same in each case. And hydrogen has stayed the same in each case. So this is not a redox reaction. And you have to do that with each one, right? And there could be more than one. So be careful with all of them. This is the culmination of this lecture, and that is to balance redox reactions. Up to now, all of the chemical reactions we've balanced, we have only focused on balancing the number and type of elements, of atoms on each side of the reaction. Redox reactions are much more complex. You also have to balance the overall charge on each side. And because electrons are being transferred in a redox reaction, you want to make sure that the number of electrons given up by one element are the same number of electrons that are received or accepted by another. So let me present the rules that you follow in balancing a redox reaction, and then we'll do an example. The first part is probably the most important part. You want to break your overall chemical reaction into what we call half reactions. So we have an oxidation half reaction and a reduction half reaction. So real quick here, what's been oxidized and what's been reduced? Well, copper has been oxidized. It's lost electrons. So the oxidation half reaction would simply start out, at least the skeleton part of it, like this. And then the reduction half reaction would start out like this. And then you would balance each of these half reactions individually. You would start by balancing the number of atoms on each side, just like you do in regular balancing. Then you want to add up the charge on each side. So real quick, for example, in this half reaction, we have a +1 charge on the reactant side and no charge at all on the product side. That's not good. Okay, there's conservation of charge here. You can't create or destroy charge. So we're going to use electrons added to either the reactant side or the product side to balance charge on both sides of the arrow. Now, once you balance each individual half reaction, we ultimately need to put them back together. But before you can do that, you have to have the electrons on each side, or for each half reaction, the same. So let's say that we added 1 electron on the reactant side to balance the overall charge. Then the other half reaction would also ideally only have 1 electron. Okay. If they have different amounts, so let's say the half reaction with copper, we had to add 2 electrons to balance the charge, which we do. And the one up here, we only added 1 electron. Then you have to multiply the half reactions by whatever integer so that the number of electrons added are the same. Okay, so for example, we added 2 electrons to the copper half reaction, 1 electron to the silver half reaction, which means you would have to multiply everything in the silver half reaction by 2 so that the electrons transferred would be equal in both half reactions. Once you do that, everything's balanced, number of electrons is the same, you can add the 2 half reactions together and you have a complete balanced redox reaction. I always kind of liked redox. They're a little bit like a puzzle. They can get very tedious and you have to be careful, but they are kind of like a puzzle. Here's a very easy example, and then I'll do one a little harder. So again, looking at this reaction I mentioned briefly on the last slide, separate it into half reactions. Okay, oxidation reduction. Balance the atoms on both sides. This one's super easy because you have one copper on both sides, one silver on both sides. It's already balanced. Balance the charge. You're going to have to really pay attention to this. This is where it gets a little bit tricky, okay? I want you to look at the oxidation half reaction. There is a charge of +2 on the product side and a charge of 0 on the reactant side. The charges have to be equal. So, and the only tool you have in your chest to make charge equal are electrons. So, but look at this. If I add 2 electrons to the product side in this half reaction, what is the overall charge on the product side now? Okay, +2 minus 2, because each electron is -1, right, equals 0. So now the charges are balanced. That's weird. That went to the next line. There. So there's the copper half reaction balanced for charge. Now look at the silver half reaction. Okay, there is a +1 charge on the reactant side and a 0 charge in the product. How do we balance that? We add 1 electron on the reactant side because -1 + 1 is 0. So here is the silver half reaction balanced. Now, I want to point out something that will help you hopefully prevent errors. One of the half reactions, it'll be the oxidation half reaction, will always have electrons on the product side to balance the charge. The reduction half reaction will always have electrons added on the reactant side to balance the charge. Okay, so they have to be on opposite sides. All right, so the number of electrons added to balance the charge are different. There are 2 in the copper half reaction, only 1 in the silver. They have to be the same before we add the 2 together. So we are now going to erase all this. We are now going to multiply the copper half reaction, the silver half reaction by 2. So that it ends up being 2 electrons. So when we do that, you got to multiply everything by 2, right? So then we get 2 silver cations, 2 electrons, and 2 solid silver atoms. So now that the electrons are the same, we can add the 2 half reactions together. And so here they are. We're going to take these 2 balanced electrons the same and simply add them together. And we get our overall balanced equation. All right, so that was a really easy example. We're going to do one that's a little more tricky, and you're going to have to practice quite a bit because some of them get super tricky. All right, here's a bit more challenging. You will typically be given the overall unbalanced reaction, okay? There are a couple more rules I'm going to present, okay, but so you're going to have to stay focused. So if you need a break, go take a break and come back and focus. All right, decide what's been oxidized and reduced. You'll typically have to assign oxidation numbers. And so let me go ahead and do that real quick. Again, these are very tedious. This is going to be one of your free response. Okay, writing net ionic reactions is one, and this is going to be another. All right, the iron cation, oxidation number +2. Permanganate ion, I'm going to give the oxygens a -2. And so since there are 4 of them, they contribute -8 overall. I also see there's a charge of -1 on the permanganate ion, so I know that everything has to add together to give me -1. Which means manganese has an oxidation number of +7 in this compound. And iron, I love individual ions because the oxidation number equals the charge, right? So these are easy. All right, so now we're done assigning oxidation numbers. Let's see what has been oxidized and what's been reduced. Well, iron has changed from +2 to +3. What does that mean? That means it's lost an electron, right? Became more positive. So if you lose an electron, you are oxidized, Leo. So iron has been oxidized. That is our oxidation half reaction. What has been reduced? Well, manganese has gone from +7 to +2. So it has gained 5 electrons. So manganese has been reduced. Right? So you only add those substances that you need to add. Okay, so sometimes there'll be extraneous reactants or products that do not participate in the oxidation reduction. You do not have to add them in your half reactions. All right, so now we have to balance each individual half reaction. Let's start with the iron one. That's going to be easiest, right? So if we look at iron, the iron atoms are balanced. It's only the charge isn't balanced, right? We have a +2 on the reactant side and a +3 on the product side. How do we get the product side to be equal to +2? We add 1 electron. Okay, +3 minus 1 is +2. And that's all we have to do to the oxidation half reaction. The other one's going to be a little trickier. All right. So let's look at it up here first. Okay. So you have to balance atoms first. If you go back to the rule, it said balance the number of atoms. So manganese is balanced. What the heck? We got oxygen on one side and not on the other. How can I just make oxygen appear? Okay. This is the important rule and the new one and what complicates life. All right, balance the oxygen atoms by adding water molecules to the appropriate side. So I need 4 oxygen atoms on the product side. So I have to add 4 water molecules so that I get 4 oxygen on the product side. Okay, very weird, I know. Okay, that's a big help because now I have 8 hydrogen atoms on the product side, right? 4 times 2. No hydrogen atoms on the reactant side. What the heck do I do now? The second important new rule. Balance hydrogen atoms by adding hydrogen ion. Okay, the reason, why can you just randomly do that? Okay, most redox reactions occur in acidic solution. And we know that the hydrogen ion is present in great quantities in acidic solution. So there are H+ ions around. That is very reasonable. So we have 8 hydrogen atoms on the product side. So we have to add 8 H+ hydrogen ions on the reactant side to balance that. All right. So now all of our atoms are balanced. So let me just circle the part that's balanced. There. All right, so if you remember the rules, it said after you balance all the atoms, balance the charge. So now be careful here. It's very easy to make a mistake. So I'm going to show this on the bottom. We're going to ignore that just for now. Okay, we're going to just add up the charges that we have. We have +8 from the hydrogen ions, -1 from the permanganate ion, right? So the charge on the reactant side, +8 minus 1, is +7. Let's check out the product side. We have +2 from the manganese ion. Water has no charge. So we have +5 on the reactant side, +2 on the product side. We need those charges to be equal. And the only tool we have is electrons, right? So if we add 5 electrons, that would be a negative charge of -5 to the reactant side, we get what? -5 plus 7 is +2, and then they'll be equal. So as always, when you have a reduction reaction, the electrons are going to be added to the reactant side, as they were here. All right, so now you have balanced your half half reduction reaction, and you have balanced your half oxidation reaction. But the next rule says that the number of electrons that you've added to each half reaction must be equal before you add them together, which means since I only have one electron in the iron half reaction, I have to multiply everything in that half reaction by 5 so that the number of electrons will end up being 5. So here we go. That's everything multiplied by 5, and now I can add the two half reactions together. This is very representative of a typical balanced redox reaction. And unfortunately, I see a typo. The electrons will always cancel out, right? So when you add these together, okay, you should have the same number of electrons on each side. Now I'm going to take just a minute and show you how to add these together. It's really simple and you may already know it, but just in case, okay? So again, these are the two half reactions that we're adding together. You literally just take all of the reactants from both of them and combine them in one long line. That's all I'm doing here. Okay, now I'm going to add all the reactants here, which is just 5 iron. Okay, then you put your arrow and you add all of the products in both. Okay, so that would be Mn2 plus 4 water, plus 5 Fe3 plus 5 electrons. Okay, and then the electrons will always cancel, okay, because there's the same number on both sides of the arrow. And you are left with the balanced redox reaction. That's it for the PowerPoint. Here is one for you to try. And if you're in Dr. Maffei's class, you got to go formative and work it out. Remember the basic rules. Start by assigning oxidation numbers. Decide what's been oxidized and what's been reduced. And break it into the half reactions and balance each one. So good luck. It takes quite a bit of practice and it can be frustrating, but stick with it.